right? That 4.32 joules has partly been converted to motion and partly been converted to elevation, right? They're two different types of energy. Angie, was that an A? Ali, sorry, Ali was assuming that all of the, excuse me, energy will be converted to kinetic energy. And she was wrong about that. If all of the energy was going to be converted to kinetic energy, then she was right. The velocity would have been 12 meters per second, because if you put 4.32 there and a half there and the mass there, 0.06, and calculate what the V must be, it comes to 12. Trust me, I've done it. Right? But in reality, some of that energy isn't there. That's not 4.2, 4.32 is a little bit less because some of the energy is down here. All right, having said all that, how do you write that in 2 sentences? Because I've just said half a page. Here's what I would say. When the spring is fully extended, it has also moved the ball up, right? Therefore, it gains some gravitational potential energy as well as kinetic energy. Right? That's probably enough. You might want to finish it off by just saying, therefore, the velocity will be lower than 12 meters per second. That's just joining the last dot. Excuse me. Part D, they're asking you to actually make that calculation. Calculate the speed. I'm just going to move that across for you. Calculate the speed at which the ball leaves the catapult when the spring is released. Okay, so we're going to figure out what it comes to. That 4.32 that was there at the beginning has now been spread amongst potential energy, gravitational potential energy and kinetic energy, just like we showed. So we're doing this. We know they both add up to 4.32, and we know everything in that list except the V. Okay, so a half, that's the mass of the ball. It's got to be in kilograms. It's not 60, it's 0.06. There it is again then, mgh. H is 15 centimeters. That's G, 9.8. The only thing you're missing is V. Solve that problem for V, right? The V turns out to be, excuse me, to be 11.87, I got. So it's only a tiny bit less than 12, but it is less than 12. Now, part E, this is a pretty obscure question. I'm just going to raise that. You don't really see this too often, but I'm glad it's here because it's a good reminder. As Ali repeatedly uses the catapult, she notices that the spring heats up and the ball now leaves the launcher traveling only at 9 meters per second because the spring's getting a little bit hot, and when you heat them up, the metal gets a little bit less springy. Excuse me. Determine the efficiency of the spring in transforming its stored energy. All right, here's the formula for efficiency of anything, right? It's what actually happens divided by what you hoped happens, right? It's the actual energy that it gives you divided by the expected energy that the physics formulas tell you that it should give you. All right, so the expected kinetic energy is a half times 0.06 times 11.87, right? So that is this bit all by itself, right? And that comes to 4.23, right? And the extra little bit there must come to the 0.09 that makes that 4.32, okay? So that's how much kinetic energy we'd expect, right? In reality, at this point, now that it's a hot spring, it's not releasing at that, it's releasing at that. So that's the new V, and you get to 2.43 joules of kinetic energy. So the actual energy that you're getting is 2.43. You're expecting 4.23. Divide the two of them, it's 0.57. Sometimes they say express this as a percentage, and that's just 57%. All right, just multiplied by 100. Right? But normally they don't. If they just say what's the efficiency, that's the answer. It's a decimal point, always between 0 and 1. Okay, and when you turn the page, you find out that this is one of those questions that just never ends, because there's a part F and there's a part G. You have to have a bit of stamina to do some of these questions. Okay, determine the magnitude of the ball's gravitational potential energy. Once it has reached its maximum height, show your working. Okay. Now this is a conservation of energy question as well. I'm just going to take you back to the original. In fact, I can draw it here. So spring with a ball on it. Spring sprung with a ball on it. So that's where we were initially. This is the point of release when it was going like crazy. And eventually it's going to get up to a certain height just before it falls back down. Excuse me. All of the kinetic energy that it has there is going to turn into potential energy, gravitational potential energy up here. And we know how much kinetic energy it had there because we calculated it just before. It was 4.23 joules of kinetic energy, if I remember rightly. Let me just check it. Yep, 4.23. So between there and there, the spring isn't touching it. That's out of the question anymore, right? We don't really need to worry about strain potential energy. This doesn't have anything to do with spring constants. The spring has done its work, right? But from there to there, 4.23 joules of motion is going to turn into 4.23 joules of elevation, right? Because at that point, when the ball stops, the V in half mv squared is going to be 0, and therefore there won't be any kinetic energy left, right? But there is still going to be the same total amount of energy because energy is conserved. So at the moment, it's 4.23 joules of kinetic energy, and up here, it's going to be 4.23 joules of gravitational potential energy. Right. So this is how we do it. Here's the, whoops. Excuse me. Here's all you have to say. You have to say what I just basically said, right? The gravitational potential energy at its highest point equals the kinetic energy at its release point. Now, I think this question is a little bit ambiguous here because I originally thought that they meant the 4.23, right? But they were carrying on from part E where it was the hot spring and it only had 2.43 joules. And I didn't realize that until I looked at the answer. So I think particularly for this question, they had to say when the heated spring had lost its potential energy or something to make sure that everyone knew that they were talking about when it only had 2.43 joules. So I think that's a little bit ambiguous. However, typically in exams, when people like me who write exams realize that it was an ambiguous question because they get people answering questions like this and they say 4.23 instead of 2.43, but they've got the meaning right. Right? People go, oh yeah, of course, that makes complete sense as well, and they would still give you full marks. Right? So if it's a bit ambiguous, if you read a question like this and you find yourself asking yourself, is that from the 2.43 or with the 4.32 or whatever, right? Just pick one of them, answer the question, right? Get the meaning right, and you'll almost certainly be given full marks, right? Because that's the questioner's fault, not yours. Rightio. Last one, trick question. State the acceleration of the ball when it reaches its maximum height. Anything that's been thrown, anything that's only hanging in the air is accelerating at 9.8 meters per second down all the time. All right, that was an easy one. Question 7, I've reproduced the diagram here. We're going to look at this fairly closely. Okay. The question says that a decorative clock is hanging from the ceiling by 2 identical ropes. There they are. The horizontal component of the force exerted by each rope is 2,100 newtons. And it says calculate the tension in each rope. Show you working. Okay, so this is what this means. Right? So clock down there, roof up there. I've just reproduced sort of this triangle here. I've just done that over here. And the orange one is what's really happening. What's really happening is there's a rope there and it's pulling the clock upwards to stop it from going down. Right? And because it's not vertical, there's a vertical component to its force, and there's also a horizontal component to its force because it's pulling it slightly to the side. Right? If you grabbed your hand and went like that and pulled that way, the clock would go up a little bit, but it would also go sideways a little bit. Right? and the sideways component of its force is 2,100 newtons. Now we've got to find out what the real force is, right? What other number makes that 2,100 newtons. And this is just trigonometry. Again, once you understand what to do, it's about grade 8 or grade 9. So what you have to do here is realize that the sine of 60, the cos of 60, you have to realize more than me, the cos of 60 is adjacent on hypotenuse. That's not opposite, it's adjacent. Right? Is adjacent on hypotenuse. Therefore, the tension in the string equals 2100 divided by the cos of 60. And the cos of 60 is a half, so that turned out to be 4,200 newtons. So each of those ropes is holding on to that with 4,200 newtons. It's feeling 4,200 newtons trying to pull it back down. All right. Now part B says determine the mass of the clock. How heavy is the clock if the ropes have to work that hard? Each of them is working that hard. All right. So the mass of the clock is m, right? And there's a formula for that force. That's mg. The force trying to pull the clock down is gravity, of course, always. That's mg. Now, because the clock isn't going down, it isn't accelerating downwards, it's not accelerating upwards either, you know that those forces must be balanced. So the force down equals the force up. And the forces up, that's this line here, right? That was the horizontal component of the tension. This is the vertical component of the tension, and that turns out to be T sine 60. That's that. This is T cos 60, if you rejig that. Okay? So, and there are two of them. There's one rope this way, one rope that way, but the vertical component of each of those triangles, because they're similar triangles, in fact they're congruent triangles, is going to be T times 60. So, the force up is 2 times T sine 60. Right? So that's the combined upward force, vertical force of those two ropes. So that must be what mg comes to as well, because it is matching mg. Right? Excuse me. So I just solved that. I just found out what that comes to, divided it by 9.8 because the g is 9.8 and the m is 742 kilograms. So that is one heavy clock. Right, 2 questions to go. Question 8 is a torque question. Okay, question 8 is a torque question. Sorry guys, I just got interrupted by something. All right. This is a situation where what is being held in place is being stopped from turning. Right? So this is a bit like a diving board. Right? They're calling it a bridge, but it's basically set up like a diving board. So I'm still going to call it a bridge though. Now, it's being held in place by these 2 pylons, the left one and the right one. But if, let's say, it dislocated from that pylon, if at point B that's separated, it wouldn't fall, it wouldn't go like that because this is in the way. But because there's more weight over there than over here, if that dislocates, what it would do is rotate. It would fall down like this. It might come loose there and then fall, but it would initially rotate. Right? And because the motion that we're trying to stop here is rotation, this is a torque question. It's not just forcing. Right? It's the effect of a force in turning something. Right? Torque is the ability of a force to turn something. So here's the situation. Specifically, the question says, Figure 6, a partly constructed bridge. It's supported by 2 pylons. The bridge has a length of 50 meters, so that whole thing is 50. The pylons are 20 meters apart, and the bridge, the horizontal bit, weighs 2,500 kilograms. Now, something you need to know. Unless they tell you otherwise, the weight of this horizontal bar can be considered to be all acting at the middle of it. Right? So it's all acting there. So that's the 2,500 kilograms. And that's not a force, by the way, that's just a mass, right? So the force equals 2,500 times 9.8. Right? And I'm just going to find out what that comes to. I think it's 24,500. Let me just double check that. Yep, 24,500 newtons. Right, so if that's 20 meters and that whole thing's 50 meters, that must be the 25 meter mark. So that little distance there is 5 meters. So that's where everything is. And question 1, it says calculate the magnitude of the force exerted on the bridge by each pylon. Show you working. This is how you do it. There's one way to do this. All right. Because this is the sort of the physics behind it. I'm doing it over here. This is the working, but this is the explanation. Right? If the bridge is not rotating, and it isn't, it's held in place. They said it's held in place. Then all of the forces that are trying to turn it clockwise must be balanced out by all of the forces that are trying to turn it anti-clockwise, or to like hold it back. All right? It's in equilibrium. It isn't working. It's in rotational equilibrium. It's not rotating clockwise, not rotating anti-clockwise. That's a bit like something not going up, not going down. The forces are balanced. Right, so here's how you do it. Over here. You start by saying that, right? Taking values around point A. Now I'm starting at point A here. I just drew point A and point B on the diagram, and I'd recommend that you do it this way, right? Once again, it's absolutely fine in the middle of an exam to add your own stuff to a diagram, right? You can say point B, point A. Right? You can point to things. You can say, refer to my annotations on the diagram. That's absolutely fine. It helps. All right, so we're pretending that it's going to rotate around A, right? If this disconnects, okay? And we're going to measure what is trying to force it that way, and we're going to counteract that with what is trying to force it this way, right? Because they must be equal, because it isn't rotating. Okay. Things that are trying to turn it horizontally, clockwise, this way, right? That is this. It's the mass of the whole thing, right? Because that mass is not centered on A, it doesn't balance. If the bridge looked, if the bridge looked like this, if that's pylon R and the bridge was perfectly balanced and that was the 25 meter mark and there was 25 meters there and 25 meters there, it wouldn't matter if the other pylon dislocated because it would just sit there perfectly balanced, but it's not. Right? Because that mass is acting at a distance, it has a torque available, right? And this is how you do it. The formula for torque goes like this. Torque equals force times the distance from the fulcrum of something that's going to turn, right? We did this earlier in the piece as well. There was a multiple choice question about it, I think. All right. So that's the force, 2,500 times 9.8. That's the distance. That's the fulcrum, and that's where the force is acting. Distance is 5 meters. So that's where the 5 is. So what's trying to turn it that way is the connection between point B and the left pylon. Right? So that must be screwed on or glued on or welded on or something, because it's not holding it up, it's holding it down. Right? It's trying to pull it back down this way. Right? This weight is trying to push it down there. This is trying to hold it down there. Right? That movement is anti-clockwise. Yeah. All right. And that's acting at a distance of 20 meters. So the torque here is acting at a distance of 20 meters. We don't know what the force is. So this is where I got that from. Right, that's F times D, and that's F times D, clockwise, anti-clockwise. Got to solve that and find FL, and it ends up being 6,125 newtons down. Right, so that is being forced downwards. That point B somehow is being pulled downwards by that pylon with a force of 6,125 newtons to keep the bridge in place. All right. So that's how much force is on the left pylon. Now I've got to do the same thing to find out the forces on the right pylon. So now we're pretending that it's going to fall. Now we're pretending that the right pylon isn't there. If the right pylon wasn't there, if you suddenly kick that one out, right, the bridge would do this. it would rotate down again, but it wouldn't be rotating like that around point A. It would be rotating around point B like this, right? Point B is now the fulcrum. It's now the middle of the rotation, okay? So again, the mass of the bridge is trying to rotate it around B like that. This pylon is pushing it back up like that. And again, because the bridge isn't moving, those two torques must be the same. They're counteracting each other. So taking values around point B, because that'll be the fulcrum of the motion if R is gone, right? That is the force trying to move it clockwise, right? mg times 25, because this point is 25 meters away from B. Okay. And FR is 20 because this point is 20 meters from B. Solve that, find this, okay? FR turns out to be 30,625 newtons up. So the right pylon, if you were the right pylon, if that pylon went and you were standing under there holding the bridge up, you would have to be pushing that bridge up with 30,625 newtons to hold it there. If that pylon was fine, but this one had gone and you were holding this bridge, firstly, you wouldn't be holding it up, you'd be holding it down because it would be trying to do this. If you're over here, it would be trying to do that. So you've got to grab it and hold it down, and you'd be holding it down with 6,125 newtons to keep it in place. That's what these answers actually mean, right? That's all you have to do as far as the answering is concerned. I just wanted to explain what all this means to you. Excuse me. All right, part B. It says a pylon can only exert a downwards force on the bridge if it's attached to the bridge using screws. Right? So a pylon can only pull a bridge down if it's using screws. Identify which pylon needs to be screwed onto the bridge. Justify your answer using evidence from part A. Okay, well, we've sort of gone through this in a fair bit of detail, that you would have to be holding this down. But how do you put that into words? This is how you put it into words. All right. So it's a bit cause and effect, right? And any question that says explain something, you have to state the cause and you have to state the effect, right? They affect each other. All right, so the weight of the bridge is trying to rotate the bridge clockwise, raising point B, right? The weight of the bridge is trying to rotate the bridge clockwise, and that would raise point B. Therefore, pylon L must hold point B down. It isn't holding it up. R is holding it up. L's holding it down. So if L is holding it down, then L needs to be screwed to the bridge to be able to hold it down. That's just joining those particular dots. Right, that's question 8. Okay, final question in this exam, question 9. Pause the video, have a good read of it, and then get back onto me. Okay, this is about an experiment that's being done. A guy called Gerald has got a boat, and he has an engine that can thrust the boat forward with different amounts of thrust, right? And he's got a table here. He's got the thrust in newtons here. He has tried thrusting the boat forward through the water with 50 newtons, 200, 250, 300, 400, right? Different amounts of power can be applied to the motor somehow, right? He has done each one 3 times, and what he has measured each of those 3 times is the acceleration of the boat, right? He's got 3 trials for each different amount of thrust. So that's what's going on. Again, there's a table, there's a picture, there's a graph. Stop and have a look at it, understand it, right? No averages have been there. I guess we have to fill that out ourselves, right? Yeah, part A, complete table 1 by calculating the average acceleration for each magnitude of thrust. Round your answers to the nearest 0.05. So do that well, right? So this is easy, right? But do the rounding, okay? I'm not going to insult your intelligence by doing those for you. I know you know how to do that. Part B is a little bit more interesting. Explain why conducting multiple trials for each magnitude of thrust enhances the precision of the data, but doesn't enhance its resolution. Right. I've made a little example here, precision. Let's worry about the resolution in a minute, right? Precision in data. Things that are precise are repeatable. Right? If I'm very precise, for example, you can be precise and still not be accurate. So if I'm throwing darts at a dartboard, there's a dartboard, and I'm aiming for the middle, and I do this, and here's where my darts go. My darts go there, 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 and there, right? That's really precise, right? You can predict where my next dart will go. It's going to go over there somewhere, right? But it's very inaccurate because I'm aiming for this. I'm a terrible shot, but I'm a really precise thrower. I'm doing exactly the same thing and getting exactly the same result pretty much every time. That's the definition of precision. Multiple trials make things more precise because they expose any outliers. Right? If you do lots of trials, we went through this in an earlier question. Right? If you do lots of trials, you find out what makes sense and what doesn't make sense, and you can take out outliers, or you can find out if your experiment is imprecise, and you can adjust something so that you don't have outliers, and so you don't have a great big spread between your trials. Right? So it exposes any outliers, and this makes the remaining data more precise. And I've got two different versions here, right? This data varies by 11, right, because it's got an outlier. There's that 10, 18, 19, 21, 19, 18, 20, 21. They're all about the same, but it's got an outlier there. Something went wrong for the 10. So they vary by a lot, right? Take out the 10, the same numbers, they vary by 3, okay? And you would have only known that that 10 was not a regular number, right? Because you did so many trials that you know what's normal, what's roughly normal. What's roughly normal is about 19 or 20. So that stands out as abnormal, so you can ignore it. All right. So resolution, this is a different thing. You have to answer both parts of this. Right? Resolution is precision in measurement. Right? So the only way to increase your precision in measurement is to get a more precise measuring implement. If you were trying to measure how far away from the dartboard, from the bullseye, my shots were, you can either do it by measuring it with your finger and go 1, 2, 2.5 finger widths, or you can get a ruler that goes down to millimeters and you can express it in millimeters. That's more precise measurement, okay? But no matter what I do with my finger width plan, I'm still going to get an imprecise answer, right? So, excuse me. So no matter how many trials I'm going to do of measuring this distance with the width of my finger, I'm not going to get any more precise, okay? Resolution, I'm not going to get any more precise with resolution, right? Resolution is precision in measurement, right? It's how accurate a measurement is. It goes more to accuracy than precision, all right? It can only be changed by changing how the measurements are taken. And if you're going to do the same thing, you're going to get the same result in that particular case. Okay. Question 3. There was a misprint in this one. So they're asking you to draw a graph. So there's a bit of information to get through here, but they say on the axis provided below, plot an acceleration versus torque graph. That was supposed to be thrust. Right? There's no torque in this question. There's nothing going around in circles. It was supposed to be thrust. Using the average acceleration calculated in part A in your graph. Okay, so you're going to graph those versus those. All right. And they tell you exactly how to get full marks. Include a scale and label on each axis, including units. Plot all the data points. I mean, you know this already, right? Sketch a line of best fit. Include uncertainty bars of plus or minus 0.05 meters per second squared. Okay, and that's an acceleration uncertainty. It's in meters per second squared, so it's going to go on the acceleration scale. All right. Have a look at the graph that they've given you in the answers, right? Rather than watch me draw it again, because it's fine. And note how it's marked as well. They gave you a list of where the marks particularly came. And let me just show you a couple of things here. Just got to catch up to myself. Here it is. Sorry, guys. Right. Okay, drawing the graph. Where are we? Here it is. Sorry. So here's the marks. There's a mark for labeling both axes, including the units. Include the units, please. It's an easy thing to miss. It's such a terrible reason to lose a mark. Right? You'd hate yourself. Right, 1 mark for using appropriate scales on both axes. In other words, the scale, if you had drawn this scale to go up to 5,000, that would be inappropriate because the biggest number you're going to record is only 400. Right? This is an appropriate scale. It starts a little bit less than the lowest number and it goes up to a little bit more than the highest number. That's how to make it appropriate. Same with this one. Right? The axes they gave you sort of forced you to put the 0 there. Right? So again, they've made this scale go a little bit bigger than the biggest number they had and a little bit smaller than the smallest number they had. Right? I don't think you have to really do this. Right? Obviously, they've put this for a reason. The reason will become obvious when you read Part C or Part D. But you can fill this out. I don't know whether you had to get the full marks. I don't think you had to really. But keep in mind, there's another mark for using more than half of each axis. So the graph has to be big, right? Don't squeeze it all down here, right? You had to use the whole thing. And again, making that stop at 500 when you know that 400 is there, that forces the graph to be big and to go out to the side, right? So, worth knowing how a graph is made. That's very typical how they do it. Okay. Next question, having drawn the graph. Part D, it says, Gerald weighs the boat and finds that the boat weighs 240 kilos. Using the gradient of the line of best fit, calculate the accuracy of the investigation. All right. Now here's how you do it. I think the way that that NEAP shows you the solution to this is a little bit confusing. I think this is a little bit easier, right? F equals ma, right? Therefore, the mass equals F divided by A. That happens to be the inverse of the gradient of this graph, right? It's the run over the rise, right? So if you look at the graph and you calculate the run over the rise, right, you'll get the gradient and that equals, you get the sort of inverse gradient and that equals M. And depending on which two points you pick, Peter Piper picked a pepper, pick a peppers. I can't even say that. My God, it's late. Depending on which 2 points you pick, you're going to get a mass of something like 200. Right? They got exactly 200 in the answers. And you compare that to what the boat really weighs, 240, and you say it's reasonably accurate, it's fairly close. It's not like half the mass, it's reasonably close. Okay, Part E, last bit. Determine the magnitude of the resistive force that acts against the boat's motion in each trial. Okay, the x-intercept of the graph is the resistance, right? Because you needed that much force before any motion happened. But the fact, let me get it back again, this is their answer. So that there is no force, no acceleration. Obviously, when the boat's just sitting in the water and the engine's off, nothing's happening. But when the boat's sitting in the water and the engine's on, and it's only doing 50, you still don't get any acceleration, right? Because this graph continues down here. And so 50 newtons of thrust isn't getting you anywhere, right? So about 75, that bit there, that looks like about 75 where it hits on this particular one, right? On their line of best fit. Yours might be a slightly different line of best fit. It's still correct, okay? But on theirs, that's about 75 newtons. So you have to get the engine, according to this graph, you have to get the engine doing 75 newtons before it even starts moving, right? So that must be the point at which it overcomes the friction of the water and finally beats it and starts accelerating. Therefore, that x-intercept is the answer. So they've given 75 newtons down there as their answer. Because your graph has probably got a slightly, you'll have the same points, but you might have drawn a slightly different line of best fit. You might not come down on 75. As long as your answer agrees with your graph, you're going to get it correct. Okay, folks, hopefully that was helpful. That is the entire NEAP 2023 Unit 2 exam. See you next time.